Here we are now in the blood chapter, part 2, still looking at the bottom here now of page 632. And we were looking at regulation and the maintenance of body temperature. And if we need to have a heat loss, then we shift the blood flow to the surface, and we notice that our children, especially when they're having a fever, are really radiating heat like crazy. But on a cold day, they're shivering, actually, and in some cases they're creating little contractures called goosebumps. Okay, then here we are over on page 633, and we're picking up the top paragraph here and continuing on with regulation. We maintain a pH, a buffered pH, in the blood of 7.4 with a very narrow range around it. So it's between 7.3 and 3.5 actually. It's very tightly controlled, 7.35 to 7.45. On average, the American diet will confer a pH of 7.35, even though 7.4 is the ideal. And the reason that we're slammed up against 7.35 is that our diet, in many cases, is predicated on meat and wheat when it comes to actual nutrients that are available, most commonly available. So wheat would include everything from bread to noodles to anything that's made with flour. So it would be pizzas and any baked goods of any kind, pancakes and crackers, so on. And then, of course, the meat component is to be found in beef, chicken, pork, and other animal constituents. So as a result, we actually have a pH it has to be buffered to get to 7.35. And if you check the urinalysis, which is basically the kidney's filtration process for the blood, then you'll notice that the urine actually has a pH of somewhere around 5 on average for many people. And so the deal is that the urine is a reflection of what's in the blood, essentially, and what's not needed to nourish the body. And the kidney has a lot of work to do to actually rid the blood of hydrogen ion. And so when we see a pH of 5 in the urine, then we know, oh, this person's kidney is really working hard. If you see a pH of 6 or 7, then you know that the person's diet is a little bit more balanced. Okay, so then maintaining adequate fluid. Of course, water is the second most important nutrient after oxygen to be delivered anywhere. And so we have the aqueous humor of the eyes, and we have all of the components, all of the systems of the body that require fluid of some kind or another. Okay, so all of our digestive processes and a lot of our biosynthetic processes are to be found in the substance of water. There's a specific protective function, and that would include preventing blood loss itself. We have a clotting system that works well, and it begins with platelets. That's the purpose of a platelet, is to close openings in blood vessels and to then initiate clotting. We have prevention of infection. We have innate and very specific adapting types of immune function. And so prevention of infection, and then ultimately the, ridding of the body of infectious agents. They begin with a description then also of the blood plasma here, and blood plasma straw-colored, is the ideal picture here. It would be the same as interstitial fluid. Interstitial fluid and blood plasma are more or less similar in some ways, at least in terms of color and consistency. It's sticky fluid because it has a lot of protein in it, and it will be a little bit sticky, the same way that how shall I say, broth from soup, from chicken soup or whatever, is going to be a little sticky. It's mostly water. It can be around 90%, it says here. I would expect there to be something of that nature in terms of the blood plasma. And the main components of blood plasma are carrier proteins, such as albumin. And of course, if you've just had a meal, then your blood is rich in nutrients, and that can be detected. In some cases, you can actually see a very serious component of fat or not, shall we say, depending on what was for dinner. And so we have carriers, chylomicrons, as well as other components, VLDLs, HDLs, LDLs. We'll get to that in this chapter at some point. Okay, so the next detail here is that they sort of get into a little discussion here of blood composition and pH and things like that. So the variations can be only slight, really, and there has to be a balance point in synchronicity, so that there's always a certain amount of whatever you need, blood glucose, or such things as oxygen and all of the hormones that are the normal constituents of blood. When we do a blood smear and we spread the cells out on a slide and we stain them with the standard stains, and usually we do a little heat fixing at the end of that stain, and then we get this result. This is a very nicely made blood slide, and you can see that most of what's going on here, these are they're called erythrocytes. They're the red blood cells, and we're just about to study those. Here are the nucleated cells. These are the white blood cells. This is a pretty large lymphocyte, actually. Lymphocytes are often not that much bigger than red blood cells because they don't have much cytoplasm. So this looks to me like an activated lymphocyte, and that's producing actually some immunoglobulin, or maybe it's functioning as a memory cell. These are the neutrophils. You can see this is a granular cell. You can just barely see faint granules there. Here are platelets, or thrombocytes. They go by two different names. So you can also, because red blood cells are so standard here, the erythrocytes, that you can actually use them as a sort of standard of measure. You can say, oh, look at that, it's about two red blood cells wide at certain points, or maybe 3 long this way and 2 that way. So you can actually sort of have a sense, an interior sense of what's going on in the blood after you've seen it a lot as a lab worker. Okay, so formed elements they describe here. We're actually going to begin directly with erythrocytes here, the red blood cell. So let's just go straight to the erythrocyte. Sometimes they're abbreviated RBCs for red blood cells. Here's a red blood cell now. In the bone marrow, these cells are formed, and then right before leaving the bone marrow, they have a collapsed nucleus. It's called a pycnotic nucleus, and it actually is, how shall I say, sort of spit out of the cell. So the nucleus is missing in the cell when it arrives in the blood. So this is already a ready-to-go red blood cell that's in the blood. You can see it's got this little dimple right here where there used to be a nucleus. It looks like a Necco wafer or something. So that's our, it's also quite flexible. It can change shape slightly in order to fit into narrow spaces.